Hello everyone, welcome to this tutorial. In the last tutorial, I have introduced how to use pw.x to do molecular structure calculations, and this is, as you can remember, this is the molecular structure calculation of carbon dioxide. Yeah, and it converges to this straight line configuration, and with a bond length that is similar to the literature. And just to notice that last time I can show you again. Last time when we draw the output, I choose this choice to reduce dimension to 0D. So in this case, you will only see the molecule, but not the whole unit cell that I use. But this time I would like to use output. Use do not reduce dimensionality, and this reflects more the actual calculation configuration. So basically, we choose a unit cell of this large, and this is a very large unit cell, and the carbon dioxide molecule lies at the corner. Since quantum espresso can only do calculations with periodic boundary conditions, so basically we have carbon dioxide molecule here at every corner, and if we choose more units to be drawn, you can see it much better. So basically we are calculating an array of carbon dioxide molecules, but since we choose a very big unit cell, so the distance between the carbon dioxide molecules are very large, so they literally do not interact with each other. So that's how we do calculations of single molecules in quantum espresso. So basically, you choose a very big unit cell. Just do it like this. Okay, so you choose a very big unit cell and put your single molecule inside. It doesn't matter whether you put at the center or at the corner; it's the same. So this is the final relaxed structure. Today, we are going to calculate the bonding energy, that is the bond dislocation energy of CO bond. So how do we do that? In principle, we know the energy of this relaxed configuration. What we still have to do is to tear the molecule apart and put the oxygens somewhere in the box, but far from the carbon, and calculate the energy. And the difference of these energies divided by 2 will be the bonding energy of one carbon oxide bond. So let's do it. Yeah. So this is the input file for last time. You can see that we used calculation relax. This time we will use a single energy calculation, that is SCF, which means self-consistent calculation. So it will not move the atoms. but it will only calculate the total energy of the current configuration. So actually we need two energies. One is dissociated carbon dioxide molecule. That is, we put carbon at the origin, and pull two oxygen atoms away from it, and yeah, this is usually enough. That is, I don't know. That is more than that is more than 7 or 8 angstrom away. And this time we will add this line here. It means that we will use Gaussian smearing during the calculations. So usually this is needed when you calculate metals, and since we tear the carbon dioxide molecule apart, it will be hard to converge. That's why we add this line to facilitate convergence. So this is the input file for the dissociated case, and we still need the energy of optimized case. So we can extract the optimized coordinates at the end of the output file that we generate last time. You can see that final coordinates and CO, and we copy it here. I already did that. And yeah, and for the for consistency, we add this line as well. Yeah. And we would like to set this ecutwfc. This is an important thing if you want to calculate the energy. If you want to calculate the structure, this is not so important. But if you like to calculate anything related to energy, this is very important. So as I said before, the larger this value is, the more accurate your result will be. So but then the calculations would be expensive, and when you increase this value further, it will saturate. So usually people do, like they increase this value and see how the total energy changes, and usually when it saturates, it is a good estimate of the total energy. So we first set it to a small value, that is 25, and we set 25 here again, and we are ready to run. Okay, so we are already in this folder, and so the program that compiled is here, .x, right? And we redirect the input file here, and type in the name that we want the output file to be, and this time I'll use AND sign at the end, because this will allow the command to run in the background, so that we can still do something in this terminal. Yeah, you can see that. Okay, we can still do it do things in this terminal. So we monitor the output file. You can see that it's calculating, and the estimated SCF accuracy is going down. Sometimes it goes up a little bit, but it generally goes down. So sometimes when you see that the estimated SCF accuracy goes up, goes down, goes up, goes down, and cannot converge, you can either lower the value of mixing beta, or your system is actually metallic, and you need to add this line. Yeah. If this line does not work, you can increase the value of this degauss, but do not use very large value of this, because it will lower the accuracy of your calculation. Yeah. And sometimes the calculation cannot converge. You have to check whether your atomic positions are correct, whether it is reasonable, whether the unit is as you wanted. Yeah. Okay. So now the job is done. We would like to calculate optimize the structure as well. Optimized. Okay. And we can also monitor the output of this. Oh, it's fast. And I already opened a chart to put in the numbers. So ecutwfc. So now it's 25. The unit is Rydberg. 1 Rydberg is around 13.6 electron volt. And this optimized Rydberg. This is the energy of the optimized. And the energy of the dissociated. Okay. Where can you find the total energy? In the output file. At the end, there's this sign and total energy. Yeah. Okay, it's here. And for the dissociated, it is as well. So there are many total energies in the output file, but when you do SCF calculations, there's only one total energy with this sign at the beginning of the line. So this is the final energy that we need. Copy it here. Okay. And we calculate the energy difference. In Rydberg, and in electron volt, that is around 13.6. Okay. And because for one carbon dioxide molecule there are 2 CO bonds, so per bond per EV would be half of the energy. And usually people would like to express bonding energy in unit kilojoule per mole per bond per kilojoule per mole, and 1 electron volt is around 96 kilojoule per mole. So it is this multiplied by 96. Okay, so we have the bonding energy of 824. But this is not the final result. We need to test the convergence of this bonding energy with respect to ecutwfc. So we change it to 50 and do the calculation again. So we change the input file ecutwfc to 50. Yeah, this is for the dissociative case, and change it to 50. This is for the optimized case. And we do these two calculations again. This is dissociative case. This will take more time because basically ecutwfc is the cutting energy of the plane wave expansion. So you increase the number of plane waves used, so you will use larger RAM space and more CPU computation power and etc. So the calculation would be more expensive, but it will be more accurate. Yeah, you can see that it starts to converge. That's very good. And yeah, this is the 21st iteration, 22nd iteration. Okay, it ends, drop down, and we are going to do the optimized calculation as well. It's very fast. I'm only using one CPU core, so if you use more cores, it will be faster. But since this is a very small system, so it does not make much sense to really use like many cores to calculate. Yeah, and we're going to copy and paste the final energy into our chart. This is the dissociated case here, and this is the optimized case. And we can see that the bonding energy changes. So you need to really test whether it converges or not. So we need to do 75 and 100 and calculate it. I'm not going to do it here. I will just I have done it, and I will just show you the results. It's here. And if we draw a chart with y-axis as the bonding energy, and x-axis has the ecutwfc. You can see that there's actually convergence here. So our estimate of the carbon oxygen bonding energy would be 795 kilojoule per mole. In literature, it is 749. So we are slightly larger. This is normal, because DFT calculations can give you an estimate of the energy, but it may not be very accurate. It will give you kind of accurate structure. Like yesterday, I showed you that the bond length, the difference of bond length is only like 1%, but for the energy, the difference is larger. So this is completely normal. But with DFT, you can surely get better results, because now we only we have limited size of the unit cell. We can expand the size of the unit cell to really isolate the molecules and etc. So there are a few things to improve, but here it's I'm just showing you how to calculate the bonding energy and the convergence with respect to ecutwfc. Yeah, and yeah. One last thing is that if you are not sure about the input file, you can find nearly everything here. So every parameter in the input file, what's the function of it, how to use it, how to specify it, you can find in this web page. So basically you can Google pw.x, and the first web page would be this, and you click inside, you can find, oh, what is the iBroth means. It means Bravais lattice index, and we use the iBroth equals 1, that is cubic, simple cubic. Okay, so this web page is very helpful. So thank you for watching, and hope to see you next time.